Okay, so welcome to this evening session. I don't know if everybody's found the complementary exercises for Chapter 8 that were handed out in the by the table over there this morning. I'm, of course, going to state the exact formulations of the problems anyway, so it's not a big business. Before starting, I have an announcement to make that the lecture note, there's an updated version of the lecture notes, which may take some time to get printed, but they're available on Christoph's homepage, and it contains everything we've done so far, including, or together with 2 of the 3 upcoming lectures. So if you're curious about what's going to happen, then you better take a look at Christoph's homepage, because these lecture notes are far more contain far more material than the ones that were handed out. So today's first exercise will be basically a check that we all have understood the same definitions. The first exercise reads, compute the revealment of majority function on 3 bits my sub 3 is the majority function on 3 bits, should not be confused with 3-my, which means iterated majority on 3 bits. But this is, this is of course the same thing as an iterated majority on 1 layer. This should be easy to calculate. So recall the definition that the revealment which we might denote delta sub f of the function f, is probability that an algorithm queries a bit x maximized over all bits x, minimized over all algorithms. So quite typically, of course, minimizing over algorithms, maximizing over bits might not be terribly hard, but minimizing over algorithms would be typically terribly hard. But this is a very easy function, so it shouldn't be hard to compute the revealment exactly. What's the very most, so what's the most naive way to calculate majority on 3 bits? Well, we've got our 3 voters here. Alice, Bob, and Charlie. And the very most naive way is to first ask Alice, what do you vote for? And she says plus, and then ask Bob, what do you vote for? And he says minus, and then ask Charlie, and he says plus. And then the plus wins. Now, this is, of course, basically as good as any algorithm in most senses, but when it comes to revealment, it has a sort of disadvantage. If we're always starting with Alice, obviously we're going to ask Alice for probability 1, which is going to give us a max of 1, which is bad. So the second most naive algorithm to calculate this thing, it's got to be something that sort of evens out. It's crucial that it sort of evens out the differences between the different bits. So a maximum should be roughly an average. Well, best thing I can think of is randomize an order of these 3 bits. So I pick a permutation at random. The permutation happens to be C, A, B. Well, then I first ask C for her vote, and then ask A for her vote, and oh, lucky day, we're already determined the function. Okay, so from here I guess you can carry out the calculations that this algorithm that I just described so this algorithm queries a bit x with probability. Well, the first 2 bits in our random order will always be queried. So first we have the probability 2/3 that the bit x is actually one of the first 2 bits. And then if it's, in case it's the 3rd bit, then we query it if and only if the first 2 guys voted differently. This happens with probability, well, 1/3 to be that x is in the last in the order, plus times 1/2 that the 2 first bits had different votes. Summed together, this gives you 5/6. This is one of the hardest words in English to pronounce to me. So this is the same, of course, for all the bits x. So the revealment of majority on 3 bits, well, technically I've only proven that it's at most 5/6. But on the other hand, now we want to prove the lower bound, so we should prove that there's no better function anywhere. That's not too hard either, right? Because any function you can think of, has to ask 2 bits in any case, because there's never a set of smaller size than 2 that determines the function's outcome. So every algorithm has to query some 2 bits, and then with probability 1/2, it also has to query the 3rd bit. So any algorithm must, on average, query 5/2 of the bits. On average, 5/2 bits. And so the probability that we query a particular one is, on average, at least 5/6. So the maximum of these probabilities must certainly be at least 5/6. This last argument I only did verbally. I hope you get the point of it. If you didn't, that's not horrible, because quite typically we won't bother to calculate the revealments exactly. We're quite happy to bound them from above. The interesting thing is finding algorithms with low revealment rather than calculating their exact revealment. Questions? So the second exercise is actually 2 exercises. We should use what we've learned today to prove that iterated majority and the tribes function are both noise sensitive. So these are, of course, sequences of functions. Which we shall prove are noise sensitive. And of course, we've already proven this a couple of times. What we want to do now is to apply what is called corollary 8.2 to prove this. So recall what corollary 8.2 says. It says that if we have a function, a sequence of functions whose revealments tend to 0, then actually the sequence is noise sensitive. So it's sort of a very, in a sense, very qualitative result, which we have some sharper quantitative versions of coming up later in this exercise session. So we want to prove that the revealments for these functions tend to 0. How do we prove that the revealments tend to 0? Well, the revealments, they're over here. They're a minimum over our algorithms. So to prove this, it suffices to find some algorithms whose revealment go to 0 and that determine these two functions. Recall the sketchy pictures of these functions. If you would go about in any way to calculate the 3 majority function, the 3 majority function, recall, the bits are the leaves down here in the bottom of the tree. Then every interior node in the tree is determined by taking the majority of its children. Any algorithm to calculate this function? Go ahead.
You simply run the majority tree algorithm for each level.
Right.
Implement centering the node by
Brilliant, brilliant. So we define this is of course a function 3 sub n. So we want to function an algorithm an to calculate this. That's a naught. Well, that's just, of course, query the bit. And once we've defined an minus 1, we define an by basically this 3 majority algorithm. So randomize an order on the children of the root. And then we run a sub n minus 1 on the 2 first ones. And if needed, so if these 2 children that I happen to choose happen to get different signs, then I also run a sub n minus 1 on the last layer. Okay. So what's the revealment of such an algorithm? The revealment of such an algorithm is, and thus the revealment of the function is at most, the revealment is, I claim, 5/6 to the k, to the power of k. Why is that? Well, because, oh well, you prove it by induction simply. I mean, you have a sequence of things here, and you prove it by induction. A naught obviously has revealment 1, which is 5/6 to the power of 1. And then what you have to do is you run two times and another half time. This lad goes to 0, so the revealment goes to 0, so the function is noise sensitive. Brilliant. The tribes example is not much more difficult, actually. It's something very similar in spirit. I mean, it's something that lies very close to the core of the function. Once again, I mean, the very most naive thing to do is to start asking from left to right until, and maybe I could stop once I found a 0 in this block, then I won't go on any longer and start querying the next block. Okay, this sounds like a perfectly good function, algorithm, except for the fact that the ones in the beginning of each block will have a fairly high probability to be queried. Again, I randomize an order in each block and then run this. So randomize order in each block. Stop when you found a 0 in each block. Since we randomize the order in each block, of course the revealment of each bit will be the same, so it suffices to prove that the probability that this algorithm queries a particular bit x, that this thing goes to 0. What's this probability? That's the probability that, well, in the random order, x is going to end up here somewhere, and x is queried if and only if we've only found a bunch of 1s over here. So what's this? This is basically the sum x can end up in this many different places. Let's call the place x ends up k, and then a half to the power of k minus 1, and I'll leave it to you to check that this indeed converges to 0. Questions? So observe that I can't point this out too many times that we actually don't use any BKS or anything here. The only sort of Fourier analysis we're using here is the expression of noise sensitivity in terms of the spectrum, but we're not using anything more than that. And the only thing we do is bound the Fourier coefficients by the revealments. Now I'd like to go on to the third question, which says, show that for transitive monotone functions, theorem 8.5 yields the same result as theorem 8.1 does for the case k equals 1. Okay, so you look through these things and convince yourself that this is true while I erase parts of the board. So this first theorem is this nice theorem by O'Donnell and Servideo, which says that for monotone functions, the cost of an algorithm to calculate it is at least the squared total influence. The cost of the algorithm is, of course, the expected number of questions, which is obviously at least n times delta of fn at all times. Delta of f. We don't have a sub n here. N is the number of bits. Question 8.1, theorem 8.1 says that in full generality, the energy spectrum of Fn on layer K is at most delta F times K to the times the squared second norm of the function f. So this is the Schramm-Steiff bound on Fourier spectrum. And what I claim is that so here we have any function, here we have any monotone Boolean function. If I ask that, if I only consider this thing in the case k equals 1 and only in the case transitive monotone Boolean, then this is essentially, then this really is the same thing. Now why is that? Well, so we add our pretty common requirement that the functions should be transitive monotone Boolean. And what happens? Well, as if we have a transitive function, if we have a Boolean function over here, sorry, let's say it maps to plus minus 1, because that's the requirement we had over there, then of course the L2 norm of it is going to be 1. And if we have a ideas? So next thing, I guess, we should do this on layer 1. So we should do this on layer 1, which means that we get an 1 there, and this is 0. What's this? This is by definition just the sum over all one element sets f hat squared of that. For a transitive function, for a transitive Boolean function, all these things will obviously be the same. So we're just going to get n times this Fourier coefficient of whatever you have there squared. Okay, sorry. A monotone function is one that's bigger on bigger inputs, right? So if you flip minuses to pluses, then the function will increase. Transitive means that all the bits play the same role. If you want to be fancy-pantsy, then you would say that it means that the automorphism group is transitive, which means that for any x, for any bit x and any bit y, there's an automorphism of the function that maps x to y. But this is essentially just another way of saying that the bits all play the same role. And in particular, of course, the Fourier coefficients of one element sets are all the same. N times f hat squared of a bit is, of course, just the total in the sum of the squared influences. What do I mean here? Right. This is, we know that for a monotone function that maps to plus minus 1, then f hats of singletons are just the influences. This we have learned. So this is the inequality that the Schramm-Steiff bound gives in this case. And in the transitive case again, this is the sum of the influences, the sum squared. Now what's that? All the influences are the same, so this will obviously be just, I guess, yeah, this will just be the sum of the squared influences times n, right? Which is n times, in our earlier notation, this thing. So suddenly the O'Donnell-Servideo bound says that the sum of the squared influences is less than or equal to the delta f. This is really the same thing. But there's something subtle here. The O'Donnell-Servideo bound was really this thing. That this thing should be smaller than or equal to the cost of any algorithm, and then it was just another inequality, a trivial inequality going down over here. So to really see that these two show the same thing, it's really, and it's the same idea that I've mentioned before, but I'll mention it once again. So we need to show or need to understand that n times delta f is really equal to the minimum overall algorithms, the cost of that algorithm. For transitive functions. And this is, of course, so this thing is the minimum overall, a expected number of questions asked, and this is by definition n times the minimum overall algorithms, the maximum probability that x is asked. So to prove this identity, we need to show that there is an algorithm that minimizes this thing that also gives the same revealment of all the bits. There's a function that is as good as any algorithm is, but that also is equally likely to query any bit. And that's exactly the same idea that we've seen before. The idea that, okay, if you've got an algorithm that you really like and that's really good in terms of having low cost, then you just start by putting up we said that the automorphism group of this Boolean function was transitive. Now pick one automorphism at random from this group. Then this is sort of gonna take away all the asymmetries between the bits and then run the algorithm afterwards. So if you've got, so you pick your, I guess you understand what I mean, right? Or you don't? Okay, so you pick a random automorphism, say sigma, and if now your algorithm tells you you should look at x, well then you just go and look at sigma of x and take that value, and you pretend like that's what x gave you, and then your algorithm will tell you, oh, go look at the 19th bit, and I will instead look at the sigma of 19th bit. So that's what I'll do. And since sigma was uniform over all automorphisms, that'll do the trick. Yeah? To a uniformly chosen one? It's not exactly the same, no. I totally agree. It follows fairly easily by sort of... Yeah. Absolutely. You can certainly have a set of automorphisms that moves, that is transitive, but that does not move any point to any point. But I'm not looking at I'm not picking uniformly from a set of automorphisms. I'm picking uniformly from the automorphism group, which really takes away all these problems. Yes, because I mean, once you have one automorphism that takes you there, then these two are going to be acted upon in the same way by the whole automorphism group, so they're going to end up spread out all over the place. Work out the details or consult a group theory book if you're unsure. But yeah, I mean, there are subtleties involved, and I, on purpose, just swept them under the rug so I could go on. Which doesn't mean you shouldn't ask questions if you're curious. Now, are you curious? You know, that's what killed the cat, so you should be a bit careful about these things. So I guess we'll move on to exercise number 4 then, which is, what can you say concerning quantitative noise sensitivity for the iterated 3-majority sequence? And what can you say about the corresponding revealments? So this is very close to something we did in class today. Where we were looking at the quantitative noise sensitivity of percolation crossings by studying the revealments. We said that so the function is noise sensitive, all right, we knew that already, but even if we use epsilon noise where epsilon tends to 0 not too quickly, then we still have a noise sensitive behavior. I would like to say something similar. If you look through your notes, maybe you could sort of transmit that proof to the iterated 3-majority setting, maybe using what we did over there. So basically, my question is, for which sequences epsilon n do we have expected value of fn omega epsilon n minus expected value of fn squared tending to 0 with n? Question marks, I guess. So I would be curious about both upper and lower bounds on how such an epsilon sequence could behave. Does anybody have any insights or any questions on what you read so far? I'm going to sort of go through it roughly now. So in the lecture we saw two different things that I would like to kind of transfer to this setting. So we saw that the sum, and now we're going to let Fn be percolation crossings. We saw that if we sum from k from 1 to n to the power of 1 over 8 plus, now minus epsilon, the energy of Fn on layer k, then that was bounded by the Schramm-Steiff bound by delta n. Delta n comes in everywhere, times the sum of k. So recall that So recall that the Fourier spectrum on the Fourier mass on level k is bounded by the revealment times k. And this is, of course, delta n times big O of n to the 1/4 minus 2 epsilon, because sum of k's up to m is m squared roughly. And we know that the revealment is of the order, if we use this this exploration path method, which is sort of two-sided and randomized, then we got a revealment of n to the 1/4. So this will be big O of n to the minus 2 epsilon tends to 0 this was what we proved in class in quick terms. And from this we concluded that if we have noise that is at least n to the minus 1 over 8, or that's slightly bigger than n to the minus 1 over 8, then we have actually this expected Fn of omega epsilon n minus expected Fn squared tends to 0. So in short terms, if we're not only is percolation crossing event noise sensitive, but it's also noise sensitive with respect to noise of the decreasing order n to the minus 1 over 8. And we also have another thing, before I'm starting to transfer over there, I'm writing down another thing. So we also have that so essentially, right, if we have no Fourier mass on low frequencies, then we're noise sensitive, and what low means in this case has to do with what sort of noise we're using on our function. And in the same way, if we have no Fourier mass on high spectrum, then that should mean roughly that this function is noise stable. So what we have in that direction is that if k is n to the 3/4 plus epsilon, we sum from n to the 3/4 plus epsilon all the way up to n. Then I don't know what's the most neat way to write this. I like to write this as by the old multiply and divide by the same thing trick, as this, which is, since we're only summing over these things that are that large, then we're getting, I can't write that like everything at once. I have to write another row. This is the sum over all sets of at least that size. F hat squared of S times the size of S over n to the 3/4 plus epsilon. Right. And this thing is obviously, now I'm only summing over large things here, but this is of course smaller than or equal to what I would get if I summed over all S's. And what I would get if I summed over all S's is just the total influence. So this is the Fourier mass on high frequencies is essentially bounded by the total influence up to a constant which depends on how high frequencies we're summing to. So from this, we have concluded that if epsilon n is much smaller than n to the minus 3/4, we have, well, we indeed have actually we have the noise stability sort of statement, probability of Fn omega different from Fn omega epsilon tends to 0 with n. But what we're really, okay, so that's a stronger statement, but we're interested in noise sensitivity rather than noise stability, so we're, actually don't think we'll ever use that. So I'll put parentheses around it rather than race, and write expected value of Fn omega epsilon minus mean of Fn squared tends to 0, cannot tend to 0 with n. I'm breaking very many chalks today and in general. Sorry about that. Okay, so here we've got some sort of two nice ideas that we might try to exploit in this other case as well. What's crucial here? Okay, so I say that exactly the same arguments, or if we like to call them calculations, give that the sum up to an of the Fourier spectrum will tend to 0 with n if an is, I guess, little o of 1 over square root revealment will do, but just so nobody can accuse me of being precise, I'll write it like this instead. And so that this was the equivalent of what was happening over here, right? So the revealment was n to the minus 1/4, and I summed up to n to the minus 1/8. So I summed up to the square root, I guess. Yeah, 1 over square root, that's right. Yeah. Of the revealment. And what happened here is basically that we're bounding in terms of total influence. Yeah, of course, I forgot to tell you here that that the total influence here is, of course, n to the 3/4. That's kind of the crucial point here. So the equivalent of this thing is that the sum from Bn up to n of this thing will tend to 0 with n if Bn is much larger than total influence of F. So what do we conclude from this? So this is something that is essentially, this is true in general for any Boolean functions, of course, but it's really, to treat this properly, we should hope that, I mean, if the total influences and the revealments are some power of n, then we can make this we're making this precise by just putting a little epsilon in the power somewhere where we find it appropriate. And hopefully that'll be the case for this majority function, right? So for the majority function, we know that the revealment is 5/6 to the k. So in this, here we get, I guess, square root 6/5 to the k. And what's the total influence of the majority function? Well, every bit has, of course, influence 1/2 to the k, right? Because probably this one is influential, pivotal, if and only if these two are different, these two are different, and these two are different. And there are 3 to the k bits, each of which have influence 1/2 to the k, so we've got something like this. Now we've got to be slightly careful about this because we've got both k and n, and these are of course not independent parameters, but n equals 3 to the k, so I guess, do you want to be careful about it? You're feeling comfortable about being able to treat this? So it means that essentially, so we know that by the same conclusion as we did in the lecture, 3 majority is noise sensitive with respect to noise. That is, if you noise it at least if you noise it at least with 1/√, delta, right? That must be what we had over there. We noise it with no, we don't noise it with square root of the revealment. We noise it with square root of the revealment. So 3 majority is noise sensitive with respect to noise that is much larger than square root 5/6 to the k, and is noise stable. Now it's unfortunate that they have the same consonant, the same initials. It's noise stable with respect to noise that is smaller than smaller than 2/3 to the k. Okay, now I want to see hands in the air now. Who would think that this is a good bound? Who would? Okay, so in the first place, yeah, right. Okay, so basically there's two questions here. Where does it stop being noise sensitive? Because we know for constant noise we are noise sensitive, and then we noise it less and less and less and less. So we have two questions. Where does it stop being noise sensitive, and where does it start being noise stable? Okay. So who would, and of course it stops being noise sensitive before it starts being noise stable. This is obvious. So who would think that it stops being noise sensitive pretty close to here? Robert, one hand in the air, lovely. Who would think that it also starts being noise stable as soon as here? Would you be so brave? Why not? Would you think that you continue indeed being noise stable all the way to over here? Anybody? Being noise sensitive, of course. Do you think you remain noise sensitive all the way down to 2/3 to the k? We've got a few hands in the air there. And then you, of course, also think that you're... And I believe everybody, except Robert, thinks that you start being noise stable at this point. Actually, it's reasonably easy to prove that you won't be noise stable until here. You won't be noise stable until here. Because what basically happens, what you basically should think of, and this will be clearer tomorrow, I think, when we talk about the spectral sample. You say that, okay, this this thing here is basically the probability that the spectral sample is above this thing, and you've shown that it and what you use here is that its mean is at least this thing, so it must have some fair probability of being above this thing. Now, it's not too hard to show you're using a second moment method that the spectral sample will actually be concentrated around n to the 3/4. So as soon as you start having some spectral mass, then you will pretty much have all the spectral mass at one point. Sorry. No, that's not it. No, that's not it. But that you actually... I'm lying. I'm only using that you actually must have some spectral mass, and it's in this picture I was meaning to point you. You can't use the second moment argument to prove that all the spectral mass would be over there, though you can in some cases, in some other functions. But you can use other methods instead. So indeed, it is. I would by now dare to say that it's true that both the noise sensitivity stops and the noise stability starts around 2/3 to the k. But to show that noise sensitivity goes on all the way until there takes some little piece of work. I have two options now. Either I try to show you an idea of how that would work, or I try to show you a better algorithm that would give a better upper bound than this one. Maybe I do both. I have 10 minutes. I'll try the first and then continue with the second. So recall that when we were looking at proving that noise sensitive, we were proving from first principles that 3 majority was noise sensitive. So we were looking at the following function. We're looking at the following function, the probability that Fn of omega f sub k of omega perhaps equals f sub k of omega epsilon, that they're both equal to 1, and we wanted to prove that this probability tended to a quarter. And what we did then was to show that AK satisfied a certain recurrence relation. If I remember correctly, it was something like 3 times AK minus 1 cubed minus 4 AK minus 1 squared plus 3/2 times AK minus 1. This may very well be wrong up to signs and constants and so, but it's something like this. I believe it's right. And what we used was some sort of fixed point argument that looks like that this is basically, so it's basically the kth power of this polynomial over here when starting from input 1/2 minus epsilon, pk of x equals 3x cubed minus 4x squared plus 3/2 x, conditioned on this being the right polynomial. And here we have the point 1/2. Here we have the point 1/4. And you start, and this is of course the graph of the polynomial. You start over here, you iterate the polynomial, and you're gonna go on and decrease until this fixed point, which shows you that AK indeed will converge to 1/4. This is the rough idea of how we proved it. Now, what happens if we're adding epsilon n noise here? Well, then we're looking in what happens after n steps, but epsilon n gets smaller and smaller and smaller, so we start closer and closer and closer to 1/2, right? And what we need to keep track of when we want to prove that this AK goes to 1/4 is that we have to somehow show that if we're allowing ourselves one more step at a time, then you're getting farther down in the sense than you are actually sending your epsilon n up over here. And this is just technical algebraic manipulations. I wouldn't want to do them myself, but I would be glad to hand them to my first year calculus class. Now, I still have 5 minutes to answer questions first, and if there's none, then I will give you a better algorithm for the iterated majority function. Anything unclear about this exercise session or the lecture today? Brilliant. I'll start erasing over here then. Oh no, I've done a terrible pedagogic didactic mistake here, because I actually wanted you to have another hands-up session on whether or not this 2/3 to the k is optimal. This is sort of wasted when I said that I would show you a better one. Who thought before I said that I will show you a better one that this was the optimal one? This was wet. It almost seems like there could be something almost like a coupling argument that would show that there's no better there's no better thing that could happen, right? But that's wrong. So who thinks there's a better algorithm already on 2 layers? Thank you. Who thinks there's not? Who thinks I will have to draw all these 27 small dashes down there? Matthijs. Thanks for believing in me. No, actually, I've got one already here for you. So, cookies for you. And now what's the moral of what might be better than the algorithm of first asking 2 random guys and then asking the third one if necessary? Well, yeah, please do. You've got an idea of what's better? Oh, okay. You have one. Please tell us.
After dealing with the first one,
Yes.
if on the first bit of the second one we see it doesn't agree, then it seems very good to move on.
Lovely, lovely. Okay, so the algorithm we had already was something like we first examine the first one, and then we examine the second one, and we pray to whoever we pray to that this will also turn up to a plus, right? So that there's a plus up on top. Now, if I evaluated the first arm of the tree, I saw a plus there, and I started evaluating here and saw a minus sign, then chances are not too good that we will succeed, so maybe I should move over here and try that one. It's fairly easy to calculate, but it's not, the calculations are not clean, but there's only finitely many choices, right? So that the expected number of questions on this tree equals 99 over 16. And we compare that to what was we had before we had a revealment of 5 over 6 to the 2, so we should compare it to 25 over 36 times 9 bits, which, for those who are quick at counting, equals 100 over 16, and this is very sort of neat numbers, I think, at least in comparison to each other. So we have at least a revealment of at most square root of 11 over 4. So what I've really proven rigorously so far is that we've got something like square root 11 over 4 over here. But I'm sure you can do better than this, but still the exact revealment of the iterated majority function is still open question. And the best, I guess you can iterate this. At first you can iterate this function and get on every second layer an algorithm which has revealment square root 11 over 4 to the k. But you could probably also iterate the idea and get something even slightly better. But it's not. But we still don't get down to the lower bound, which is the last thing I should point out for you today. That the O'Donnell-Servedio bound gives you that the total influence squared is at most n times the revealment of any function. That's the O'Donnell-Servedio bound. What's this in this case? This is n is 3 to the k. The total influence is 2/3 times, right? We have the influences squared of 4 over 9 to the k, and we multiply by 3 to the k, so this is no. The influences squared are 1 over 4 to the k. We have 3 to the k. We should have something like this. This should be it. So the O'Donnell-Savedio bound gives you that you can't get a better equivalent than 3/4 to the k, and where between 3/4 and square root of 11/4 the truth lies is still open. Okay. Questions? Otherwise, we take questions outside, and have a good night, everybody.